So today we're going to talk about stress. This is a fundamentally critical concept in deciding whether or not things are going to break. How much stress can a material take, and how do we calculate how much stress it's under? So the most simplest concept is that of a single member in what we call axial tension. So this is a force F that's applied, stretching the member that way. There's got to be an equal and opposite force on the other end. Otherwise, this thing would fly off in that direction. So it's balanced by these two opposing forces. And we want to calculate just how hard we are stressing this material. So let's just imagine a cut plane through the middle of this member. We could even cut it in your mind and glue it back together and think about what does this glue have to do to keep these two halves stuck together. That's, in fact, what the molecules that comprise this member have to do to hold it together and keep it from failing. So we're going to answer the question, when does it break? So this starts with calculating stress. We'll use the symbol sigma for stress. That's the Greek letter for S. And it's the force per area. Obviously, something with a lot more cross-sectional area can withstand a greater force. And so the dimensions of this will be newtons per meter squared. And this is also known as a Pascal. So, most materials, when you apply a stress to them, behave like this figure shown here on the left. Let me explain this x-axis first of all. It's not really the amount of stretch that matters. If I'm pulling on this bar and it stretches a centimeter, that's really a very, very different experience than if we had a bar a kilometer long and we stretched it a centimeter. What really matters is not the stretch, but the stretch per length. And that is called the strain. That got cut off a little bit, so I'll just define it again over here. Strain is the stretch per length. So it's often given either dimensionless or it's given as a percentage. So as it happens, oftentimes we put strain on the x-axis. That's just customary. But what happens is for small amounts of strain, and this is what's called elastic strain, you get a very linear behavior. This is called Hooke's law. It's just very simple. You pull on it and it snaps back, and you can operate in here for a long time, just going back and forth. And you won't have any problems with failure. But you're going to get to a point, and this is called the yield stress. And with this yield stress, things change fundamentally. You no longer have this linear behavior, and you're plastically deforming your solid, which means it's not going to snap back the way it was ever. And a very simple example, and I have this in my hands, it's probably a little small for you to see, it's just a paper clip. If I take this paper clip and I stretch it, made it like an S, it's not going to go back ever exactly the way it was. And it's actually gotten weaker. So if I just bend it a few times back and forth, it gets so weak that it breaks. And my paper clip broke. Similarly, this yield stress, what happens with the slope going down now is it doesn't take much more stress for you to get a lot more strain. And it will start stretching a lot more, and it will break at not much more than the yield stress. So this is the stress that you want to stay below in your design. You want to stay well below it, as a matter of fact. Now, what this yield stress is, well, that depends on your material. It depends on whether it's aluminum or steel, what kind of steel, whether it was heat treated, whether it was annealed, cold rolled, whether it's plastic, whether it's damaged. All these things matter. So, I'm sure you all remember Murphy's Law. You may also remember your Shakespeare. One of my favorite lines in Hamlet. Hamlet says, "There are more things between heaven and earth than are dreamed of in your philosophy." So what that means is that this is a very idealized diagram. Your material may not be quite at the exact yield strength, may not be able to sustain this. Your calculation probably made some simplifications. It's not spot on. There's all sorts of things that could go wrong that we haven't imagined. So because of that, when we do these calculations, we use a factor of safety. And it's a very simple concept. So instead of using yield strength, as your design criteria, let's put in some margin of error. A factor of safety of 5 would be over 5. Or, put another way, if you calculate the stress in your device, and it's only going to experience 1/5 the yield strength, you say, okay, I've got a factor of safety of 5. And in life-critical designs, it's common to have like a factor of safety of 10. Right? You don't want to come anywhere close to killing somebody. All right. Now, there's all kinds of stress. I'm sure you know that now that you're a college freshman. We're going to talk about something called hoop stress, which is a common stress that we're particularly concerned about in our design process. With hoop stress, let's just imagine that we've got a long cylinder, or cylindrical vessel, actually. It's containing something that's pressurized. So this might just be a pipe. And we're going to assume the pipe has pretty thin walls. So here's our pipe. And in your energy extraction device, you may have some pressurized tubing or pipes, and this should be something that you want to analyze. Will it break? Can it sustain the pressures that you'll be subjecting it to? So our pipe has some length, let's call it L. It's got a radius, and we'll call that R. And I'm not so concerned with whether we're measuring the radius to the inside of the tubing or to the outside or somewhere halfway in between, because we've assumed, or we're going to assume, that this is a thin-walled tube. So this thickness of the wall, we're going to assume that that thickness is much, much less than the radius. Now, in truth, you don't just have pressure on the inside of your vessel. You're going to have at least atmospheric pressure, I expect, on the outside. So for that reason, you really have a balance. But it's the net force that matters to us. And so we are going to use gauge pressure. And this means we're using pressure relative to atmospheric. And this is a familiar concept to you. If you've pumped up your bicycle tire and looked at the pressure gauge on your pump, it's telling you gauge pressure. When it says 0, it doesn't mean that there's no molecules of air in there. It means you're at atmospheric. And when you are at 3 bar, if you've got a metric bicycle pump, then you're at 3 bar above atmospheric pressure. And that's what we call gauge pressure. So that's what we're going to use here. All right. So next what we're going to do is we're going to calculate the stress in this thin-walled vessel. Because once we calculate the stress, we can compare it to the material's yield stress and see if we need to worry. So let's, again, sort of like that tensile member, let's cut this in half, but we're going to do it this way. We're going to cut through the walls. And when we do that, we get a semicircle on the end. There you go. So the stress exists here in these thin walls. On both sides, as a matter of fact. That's what's holding this together. So again, imagine we've done a fictitious cut. We're going to put glue in here and see what that glue needs to sustain. That's what the molecular bonds have to do here of this wall material. How hard do they need to stick to each other to oppose the pressure force that's trying to push this thing apart? So I'm going to draw just a few big arrows here that the pressure acts on this whole cut surface. Like that. So the force due to the pressure is equal to pressure times area. Pressure is measured in force per area, so you multiply it by an area and you get a force. All right, so this is an example of letting units be our guide. So the force here is pressure times area. And that area, well, is the area of this rectangle. And it's got, on this side, 2r for the width, and then for the length is L. Now, let's come back to the walls here. The force that's holding this thing together is equal to the stress, because that's force per area, times the area of this thin section here, which is the thickness times the length. This is a little thin rectangle, but there's two of them. There's one on either side, so there's a 2 here. Now, this pressure vessel is in static equilibrium. If it's not bursting apart yet, then those two forces are equal and opposite. So let's do that. Let's just set them equal to each other. Now the L's cancel out. Oops, the T's do not. Sorry, the 2's cancel out. And we have this simple relationship. So some things are fairly obvious. As the pressure goes up, the stress goes up. You double the pressure, you double the stress. You could probably figure out, or have anticipated, that thinner walls means more stress. What you might not have guessed is a bigger radius means more stress. If you're going to deal with high pressure, you want to do it in a small radius pipe. High pressure tubing has a small radius. Now this result is unique for cylinders. If you're going to do other shapes, like say a spherical pressure vessel, it's a slightly different calculation, but you can just follow the general idea here. The other thing, and this comes back to the factor of safety, we didn't include everything here. If there's end caps on this, there's an axial stress too, a stress in that direction. So this is not going to be the spot-on calculation. And in truth, we assumed thin walls. If the walls are thicker, if they're substantially thick compared to the radius, then your calculation of stress is going to be a little bit off. Now let's do an example. So let's do PVC pipe. And we're going to say our pipe has a radius of 5 centimeters. This is a pretty fat pipe. And a thickness of 2 millimeters. And we want to know, will it hold a pressure of 3.5 atmospheres gauge? So let's just use that formula over there. Now, if you remember from our discussion of units, you'll understand what I'm doing here as I convert. And I'm going to keep track of the units here the whole way. So 3.5 atmospheres times 5 centimeters over 2 millimeters. Now, these are both lengths, and if they were measured both in centimeters, those centimeters would cancel. So let's convert this to centimeters. And nobody characterizes material properties using atmospheres. Stress is in pascals or psi, but not atmospheres. So let's convert 1 atmosphere to a Newton per meter squared. That's the same as a Pascal. So if I plug that in, I get 8.87 times 10 to the 6 pascals, or 8.87 megapascals. Now, if I look up the yield strength for PVC, (7,500 psi). So we have some old-fashioned units to deal with here. So let's convert that to SI units. So I happen to remember that 1 atmosphere is 14.7 psi, and it also is 101.325 pascals. And that gives me a yield strength of 51.7 megapascals. So let's compare them. So, looks like we're safe. As a matter of fact, if we calculate the factor of safety, if we divide this by this, we get our factor of safety is in excess of 6. So that's probably okay. All right, so that's how we calculate stress. Get it right, be safe, see you next time.